Hello everyone, today in this video we'll be discussing the module 3 of microcontrollers, and in this video we have the following topics: C compilers and optimization. So we'll be learning what is the optimization and how a code is compiled from the C code to ARM code. Okay, so we'll be learning all of these things. So let's get started, and before starting please do like and subscribe. It helps me make more videos like this, and if you watch this video till the end you can easily score more than 80% marks in the exam. So don't miss any of these topics, and if you have any questions you can DM me on Instagram. The first topic is overview of C compilers and optimization. Okay, what is optimization? It means making better. So previously, if you had iPhone 13 and you optimized it and made iPhone 14, then that means you have done an optimization, right? So that is called as optimization. Optimizing is worth only when the most frequently executed code is optimized. Okay, so if this is the code and this part of the code is running in repeat, okay, if you optimize this part, it will reduce more time, right, than optimizing some other part because that is not executed more frequently. And profiling tools are used to find the most frequently executed code snippets. If this is the code given, if I use profiling tool, it will tell me which lines of code will be which lines of code are actually repeating more times. That it will tell me so that I can optimize the following codes. Okay, so that is the profiling tools. Now, basic C data types. ARM handles the basic C data types via various addressing modes and instructions. Okay, so to work with any data, we need to identify what is its type, right? Data type. So based on the data type and the instructions, the operations will be performed. Okay, if the architecture is pre-ARM v4 or ARM v4 or ARM v5, the following instructions are used. Okay, it loads and stores unsigned or signed values of 8, 32, and 64 bits. Okay, and the following are the data types used in C. Char is used, short is used, int is used, long is used, and long is used. Okay, so this is related to the size of the data. Now, local variable type. Local variable type means if you write a code, if you write a variable within a code snippet, that is called as a local variable because that variable can be accessed within this scope. ARM v4 based processors can load and store. Okay, it can both load the variables and store the values of 8, 16, and 32-bit data. Okay, and local variable should not be used as char type. Okay, char you should not use for the local variables because it will be an unsigned, and if it is unsigned you cannot compare it with 0. Okay, let's understand. And the loop will never terminate. What I mean to say is, this is an example. Okay, this is a checksum. Checksum means what? We are calculating sum of the data. Okay, suppose that I have the number 127. Okay, checksum of this is 1 plus 2 plus 7, that is equal to 10. Okay, so adding up each digit, so the digit is taken into the data here and each data part is getting added as sum. Okay, so this is the function which is performing that. Now in the local variables I have used char I. If you observe carefully, char I is used instead of int I, and char is put as 0. And as you know, char is taking up one space in the memory and int takes up two spaces, right? So you might think that it's taking less space. Now is it's better, right? That is the initial assumption, that it is better, but it is not better. Why? Because when I becomes 255 and attempted to increase, it becomes 0 because char's limit is from 0 to 255 only. After 255 it comes back to 0. If I have more than 255, it will not consider it, it will come back to 0, right? So that is not the expected thing that should happen. So that's why in the compile instruction, see, there are two things. Okay, this is the normal code which will be there in the C, and that will be converted to the ARM instructions, which is a compile instruction. So it will look like this, the same thing. So here we have three variables, R2, R0, and R1, where I is 0 is stored in R1, sum is 0 is stored in R0, and R2's value is storing the data, whatever we pass, like 127, right? 1 plus 2 is plus 7 we have to do. So in the loop, what happens? First, we are loading the data into R3, the first digit of it, and we are incrementing the value of I, and I is converted to the char value. Then comparison happens between I and 64, and the sum is happening here. Okay, and if I is less than 64, again loop it. Okay, so this is the code which is happening here. But if you see, it is in a char, and the comparison will be done only till 255. After that, it will not take place. When we declare it as I as unsigned int, okay, if we declare it as unsigned int, at that time that restriction will be removed, and we have to do one extra instruction, R1 plus plus. But this extra instruction cost will be more beneficial than not putting this instruction and using it as a char and leading to the just the range of 255. Okay, so to overcome that, we'll be using an int. Second thing, we'll be using a unsigned int. Okay, so that it will not give us the problem of comparing it with 0. Okay, so in the first snippet you can see that R1 are OX 0x44 instruction to make the range of I from 0 to 255. This instruction is not present in the second snippet because unsigned int is used. In the first thing, if you can see here, this line of code is used, right? This line of code is for converting from the value which is present in the register to the char value. Okay, this is to ensure the range 0 to 255. Okay, but that is not present here because in unsigned int it will automatically assume that range. Okay, next, if the data bit contains 16 values, okay, 16 bit checksum, the following code is written. Okay, if it is 16 bit checksum, it has to be converted to short because 16 bit cannot be stored in the data type as char or int. Okay, because as we seen above, here in the data types, 16 bit is cannot be stored in the char. Okay, it has to be in the short, then, or it can be stored in the int also, but at least short has to be used. So 16 bit, it should be converted to short. Okay, so the conversion happens here, that is called as typecasting. Okay, as you can see, this line of code is written at this line typecasting is used. Okay, and the updated code snippet would be as follows, and as you can observe, there will be a short here, so it will be converting to a short value and then it will be storing, because if you don't convert to short value, only half value will be stored, only 8 bit will be stored, other 8 bits there will be no space to store. Okay, now, but we are converting this into the short value, and it is increasing the number of instructions, but it is necessary because the LDRH does not have addressing modes to offset directly like LDR in V2. Okay, we are have to convert it because LDRH does not have that many addressing modes as LDR. Previously we used to use LDR. Okay, here we are using LDRH because we are using the short value, and typecasting requires two move instructions. As you can see in the typecasting, when we are doing typecasting here, right? Before that there are two instructions extra coming here. So how many instructions extra came? Three instructions extra came, but it will still give us better performance than the previous one. Okay, that's the key point. Now again, optimizing it, we'll be using the pointer to do the operations here. Okay, and that will also reduce a bit further, and it will be better in performing. Okay, so here we are not doing any conversions except at the last place where we are doing the conversion here, but we are using the pointer. Okay, and we are converting it to LDRSH instead of LDRH. Okay, so it is giving better performance, still performing 1 cast to 16-bit integer on the function return. Okay, so that was about the data types. Now let's have a look at the function argument type. Till now we discussed some variable is there, we want to store in it in a place, and that place which type it should be, because type decides how much long it will be, right? So if more data is there, I have to store in a bigger data type. Okay, now we are discussing about function argument type. Means when a function is called, the arguments are nothing but what is passed here. Okay, that is called function argument, and return means whatever the value we are returning finally, that is called as a return value. Okay, so consider this example where we are taking two numbers a and b, and we are calculating the half, means average of a and b. Okay, so this is the code where you're performing the left shift operator. Okay, now the function argument passed are of type short, and return value is kept to be short itself. Okay, so here short is there, here short is there, so return value also it's expected to be in short only, but based on typecasting the return value might change. Okay, it can become wide or narrow. Okay, wide means if the values which are here, it is of smaller data type and answer is of bigger data type, so it will become a bigger data type and return it. And if it is the reverse case, if these answers are bigger but the small answer is shorter, the final answer, it will narrow it down to the shorter data type. Okay, so this is called as the typecasting. Okay, and below assembly code, the return value is typecasted to short. Okay, explicitly we typecast it to short, but the arguments remain unchanged. Still, if after getting the answer, this still remains short only, but we need not have this anymore, so we can convert it into some other things as well. Okay, some other types which are more efficient. So here, as you can see, here int a is just it is taking automatically, and short we are explicitly doing it, so it becomes short here. Okay, now more modified version where the arguments are also typecast to be more cautious. So here we are typecasting the arguments as well explicitly. We are taking it differently. Okay, in different lines of code, first we are converting I to int, and then we are converting this also into int. B and a, both we are converting into int, and final answer will be in the short, because that's the range. The final answer is not needing the range for the int, it is just requiring short. Int is greater. Okay, int means it is the value 2, and short means it is the value 1. Okay, so when we are dividing something, suppose 10 divided by 2, it became 5, right? 10 has 2 digits and 5 has 1 digit, so int is getting converted into short. So we need to be sure to explicitly mention it, so that it will not take more space and unwanted memory. Okay, so it will become more optimal. Okay, so that was about the function argument types. The next one is the signed and unsigned types. Okay, what do you mean by signed? Signed means there is some value like 32,000. Okay, 32 minus 32,000 to 32,000. Okay, this much range numbers it can store from minus 32,000 to 32,000. Okay, that is called as signed value. Unsigned means there will be no sign, minus will not be there. So what will happen? I cannot store negative values. I'll be just able to store from 0 to 32,000. But what about the negative values? Instead of the negative values, I can put it in front of this so that I can store another 32,000 values in positive digits only. So it will become 0 to 32,000 to 64,000. So total range will be from 0 to 64,000. Okay, in the negative range also I'm putting it in positive. So that is unsigned. Okay, unsigned will have longer values and signed will be having the sign, so it will have shorter values. Okay, and to perform the division, unsigned value gives us the better performance. Okay, remember this. Only in division operation, multiplication, addition, subtraction, signed values are better, but unsigned is better in the division operation. Okay, an example is given here when we are taking two integers and dividing by 2. Okay, so here the following the code is written. First we do a plus b, and then we increment the value of r naught, and then we do the left shift operator so that it divides by 2. Okay, sorry, this is the right shift operator. Okay, so it's dividing by 2. Okay, and in this case if we use unsigned, it is more better. Why? Because if we use signed, what happens if minus 3 is added with 2, what it will become? Minus 1. It comes closer to 0, right, when we add some value. But if we do minus 3 divided by plus 2, so it will become what? Minus 1.5. But minus 1.5 is more closer to minus 8. Okay, the arithmetic round shift rounds towards minus 8. Okay, minus 8 in the sense it is talking about the number of digits in the zeros. Okay, the division counts towards 0, but arithmetic right shift counts towards the number of zeros in the right. Okay, so basically you need to know that when we are using division, you need to use unsigned int, and this is the example you can write in the exam. Okay, and avoid the char and short types for function arguments and return value. For both the function argument and return value, we have to avoid using char and short types. Use int values, and it will be more better if you use unsigned int to avoid unnecessary typecasts and missing of the values. Okay, next, C looping structures. This section will be discussing about the most efficient ways of coding for and while loops. Okay, for loop means what? For, if I put I is equal to 0 till I is equal to 10, print a. Okay, so what will happen? A will be printed from the 10 times. A will be printed 0 time, 1 time, 2 time, 3 time, 4 time, and 10th time. Like that, it will print a 10 times. Okay, that is called as a loop. Now there are two types of loop: for loop and while loop. Okay, how do we use the efficient ways to code the for and while loop in the ARM compiler? Okay, so here is an example. Here is a for loop. As you can see, it is starting from 0, it's less than 64, it's getting updated, and some operation is happening here. I plus plus is happening. If you convert the same into the ARM code, this will be the ARM code here. And if you observe, there are three instructions which is happening here: an add to increment I. Okay, I plus plus is happening, which is the instruction add to increment the I value. A comparison is happening where we check if the value is less than 64, and a conditional branch should loop if I is less than 64. Go to loop. Loop means again start from here. Got the point? There are three instructions happening here, but this is not efficient. On an ARM, a loop should only use two instructions: a subtract to decrement the loop counter. Now in the looping part, decrement is more better than increment. Okay, why it is, I'll tell you. Which also sets the condition code flags on the result construction conditional blank instruction. And key point is that loop counter should count down from to 0 rather than counting up to an arbitrary limit. So the count should not actually be from 0 to 64, it should be the reverse one, it should be from 64 to 0. Okay, this is more better. Why this is better? It is because we are comparing it with 0, and 0 has a specific flag. Okay, other numbers don't have a flag. There is a 0 flag, Z flag. Okay, and if it is capital means the value is 0, if it is small means it is not 0. So basically we just need to check the flag instead of comparing if the number is 0 or not. And checking the flag is easier than comparing. I'll repeat, checking the flag is easier and less time consuming than comparing the numbers. Okay, so that's why we have to always use the decrementing count. It will improve the performance. Okay, so an example is here. If 64 is here, and until it is not equal to 0, we are comparing it. Okay, means we are decrementing and doing the operation, and when it is 0, it will stop. Now here the performance is increased because we are not actually comparing I with 0, we are just checking if Z flag is true or false. Okay, and it will be less time consuming. And this is the same thing here, we are setting the flags and comparing. Okay, Now we can use the for loops or the while loop, do while loop with a variable number of instructions. Now here the number of times it will execute is 64. We all know it because it is starting from 64 to 0. But what if it is a random number n? We don't know the value of n, right? Or a condition, if it is until the condition is true, we have to execute. So in that case, we are using a for loop without a initialized variable, and we are using n value here. Whatever is the n value passed, that will be compared. Okay. So this is the equivalent to the ARM compiler code for the same above thing. And this is one way where we can use the loops with variable number of instructions. The number of instructions we don't know, it depends on the value of n here. Okay. And if you use the same thing in do while loop, it will be as follows. We will be having a do here, and whatever is the condition is done, and while minus n not equal to 0, the n value is also decremented and it is compared within a single line, and that is more efficient. Okay, it will save a lot of time. Now we can use the loop unrolling to improve the performance. What does loop unrolling mean? So suppose that I have a code which what it does is it will do the following operation. Sum plus is equal to star data plus. Okay, some operation it is doing, and it is doing suppose 64 times. Now instead of 64 times, I'll just run this loop 16 times, and what I do, I'll write this same line 4 times. So what will happen? Every time it will run 4 times, and like that it will happen 16 times. So 16 to 4, it will still be 64 only, but it is observed that if you do it like this, it is more performance, the performance is more better. And this concept is called as loop unrolling. Unrolling means repeating the numbers and reducing the number of iterations, that is improving the performance. And the equivalent compiler code is given here. Okay, just the same code is getting repeated here. Okay, again sum plus is equal to 3, sum plus is equal to 3, sum plus is equal to 3. Okay. Now, as you can see here, there is a reduction in the data size also, but it is not always the case. It is only efficient when it is gain is more than 1%. If it is less than 1%, means the code which you have written, it is not repeating much and it is not giving us more time savings, then it is not efficient to increase the number of lines of code for less reduction in time. The number of lines of code, even if it is increasing, it should ensure that more than 1% the time should decrease. Okay, total time it should improve by 1%, then only it is worth it. Okay. Now, register allocation means what? Whenever you assign a variable, like we will be writing int x is equal to this, int y is equal to this without thinking anything, but computer behind the scenes is working to allocate the registers for each of these. So if you mindlessly put unlimited or very more number of variables, what will happen? The compiler will be not able to allocate all the variables, and there will be happening a variable spill. Like that, it will be a bottle will be there inside the memory, and bottle will be spilling all the variables. Okay, your variables will be going here and there, and you will be getting a lot of errors in the code. You will be accessing some variable value, but that variable will not exist anymore. So that kind of things will happen if you stupidly put all the variables whatever you can, and for everything you are using variable. In that case, it will be negative consequences. Okay, so there are only 15 registers, so use it accordingly. Okay, and few registers are already there, which is to for a specific purpose. Okay, the purpose is also given here, you can go through it. Okay, so try to limit the number of local variables in the internal loop of functions to 12. Okay, try to limit it to 12, and compiler should be able to allocate these to ARM registers. You can guide the compiler as to which variables are important by ensuring these variables are used within the innermost loop. That feature is also there, so that if you have allocated more than 12, you can tell which are the most important 12, so that there will be no variable spilling. Okay, now function calls means we are calling a function. Okay, there is a function defined, and this is the main code, and if you want to do some operation with the function, you'll be calling it, and it will be returning a value after its execution. That is called as a function call, and while calling the function, you'll be passing some values, that is called as function arguments. Okay, now the first four integer arguments passed in the four ARM registers are not r1, r2 and r3. Four arguments which you pass, like if you write the function and you'll write a b c d, you're passing these four values, and these values will be stored in the registers r0 to r3. Cool. Now the subsequent if you are passing more arguments like d e f g h I, like that you are passing, it will be stored in a stack. Okay, so the better is to store it in the registers only, because it will be fast for accessing. If you pass more unwanted variables, it will just cause more time and more memory allocations. Okay, so try to keep the arguments as less as possible. That is the most optimal code. Okay, so try to restrict the functions to 4 arguments. This will make them more efficient to call. Define small functions. The compiler can optimize the function call, and critical functions can be inlined using inline keyword. Inline mean instead of writing a separate function, we are writing the same function in one line only, so that instead of calling and coming back, it will do the operation there itself. That is called as inline. Okay, so this is the summary you need to keep in mind for calling the functions efficiently. Okay, The last topic is the pointer aliasing. Aliasing means what? Aliasing means if two pointers are there and it's pointing to the same address. Pointer what it does? It will point to some address. Pointer aliasing means two pointers pointing to the same address. Okay, the pointers are set to alias when they point to the same address. Compiler does not know which pointers are aliasing. Compiler does not know which all you have put it to point to the same address. Compiler will just say it is pointing to this, it is pointing to this, it is pointing to this. But it is not that intelligent to know these all are pointing to the same thing. Okay, that is a limitation of compiler. But we are not as stupid as the compiler, right? We know that it is pointing to the same thing, so we can optimize it by, instead of, if all are compiling to the same thing, why you need three things? You can just use one thing to perform all the operations, right? So the example is given here. Timer 1 and timer 2 both are pointing to step. Okay, and what happens is when you are accessing the value of step here, and compiler is again accessing the value of step two times. Okay, instead of this, what you can do, you can use a structure. Okay, structure means it will keep both things in the same place, so that compiler will know these both are pointing to the step only, so that it will not do two operations back to back. Okay, that is called as a pointer aliasing. And how can we use that feature to optimize our code so that it performs in lesser time? Okay, and avoid pointer aliasing. First of all, avoid pointer aliasing if you can avoid, but if it's still necessary, do what I have told you to do. Okay, do not rely on the compiler to eliminate. Okay, compiler is stupid. Okay, it will not know what to eliminate, so you have to tell it. Okay, and it ensures expression is evaluated only once. You have to ensure that if two or three things are pointing to the same thing, one thing should be sufficient for the whole operation. Avoid taking the address of local variables. The variables may be inefficient to access from then on. Okay, always you try to use the global variable so that it can be able to access from anywhere, and avoid taking the address of local variables. The last one is the portability issues. So here are some issues you encounter when porting C code to the program. We will be writing C code and we'll be easily giving the command compile. Okay, but and we'll be waiting. But inside the system, there will be many things happening, and errors can also happen. So there are totally main 8 errors that can happen. I'll take you through each of them. Okay, so first is unsigned char cannot be used for comparing with zero. Okay, unsigned values cannot be compared with zero. This is the thing I told you in the first part of the module also. Now also I'm telling it cannot be used to compare with zero. Second, 16-bit to 32-bit addressing changing or the architecture switching can also cause the issues. A C program can manipulate pointers to make it from char star to int star. Okay, so it becomes like unaligned. And if the functions are not prototyped correctly, they may return wrong answers. So it is your duty to prototype it correctly. Prototype means which type it is and what are the function arguments getting passed, type of these arguments, and after the operations you'll be returning some value. What is the return type of that value? All these things should be prototyped properly. Okay, and what's the whole structure of the program? I mean the function that has to be having a prototype so that the compiler will know that such a function exists. Okay, so if something is missed, it might cause a issue and it will return a wrong answer. If the C code assumes the bits are laid out in a certain order, okay, you try to hide this fact as much as you can. But if the C code thinks that you are putting the bits in a certain order, like all the one bits here, then the two bits here, then it will not be portable. Okay, so it is having some attitude issues. Why? Because C code, if it thinking that you are just putting the codes in the order so that you are insulting the C code, it cannot handle unordered bits. Okay, like that it will take it into personally, and the code will not be portable. Okay, so this is another issue. Next is you can't cross-link libraries and code between different compilers. This is compiler C1, this is compiler C2. The cross-linking cannot be done between the different codes and libraries, one compiler for one program. Okay, and volatile keyword prevents compiler from optimizing. Cannot use the volatile keyword and expect it to be optimized as well. And using inline reduces portability between different architectures. Inline may increase the performance, but it will reduce the portability. Portability means if you want to execute your program in print system and you put that program in USB and you put it in his system, his is a different system, 32-bit, and yours was 64-bit. So what will happen? It will not execute properly here. Okay, because of the inline keyword. So these are some of the issues, but this is not very much frequently occurring ones. Okay, but it exists. Okay, that's all from this module. And if you found this video helpful, please like and subscribe. It helps me make more videos like this. And thank you so much for watching. I'll see you in the next one.